All right, welcome back. So we're going to have a go at the rest of this question. Now we could just jump straight down to here and see if there's a point of inflection. We could go immediately to this, and this would tell us the nature of these points. But there's the alternative way is just to walk through and divide up into intervals, and I'm going to do that because it's part of what you do in your development. So we've got all of the values, so it should be fairly straightforward for us to divide up an interval set. So I'll just do it up the top here. And each of the values that we're looking at are -2 and -1 and 0 and 2. So we're looking to see what the values are, different values of x, and the impact on the derivative. So what about x is less than 2 in this interval? So x is less than 2. What will be the first derivative looking like here? For x is -2, we'll have an interval there. So we'll put a bit of a blind interval down here. Extend those down. Actually, I might just put f dash of x there. Use it there. There's our x values. And so we're looking at these intervals. Okay, x is equal to 2. -2 there. X is in the interval of -2 to -1. But we also want to have a look at x equals -1. Then the interval, -1, x, 0. But it'd be nice to have a look at x is 0. See if it's different, because not every x value impacts. And so then we'll go from 0 to 1. That could probably be one interval. Well, we're having a look. Also, we want to have a know what happens at x equals 1 and at 1 to 2 and at 2, and then x is greater than 2. So what's happening to the derivative at all of those different points? What's f dash doing? Okay, what's f dash doing? So we would have to test some values. So we would have to pick something like -3. And all we're looking to do is put it into the derivative equation and see what -3 would give us. All we're looking to do here is pick something like -1.5. Doesn't matter what the particular value is. There we've got -1. Here we've got, say, maybe -0.5, -0.5. 0 we can check. 0 to 1, maybe we'll check a half. 1 we want to have a look at. Maybe 1.5, 1.5. And something greater than 2, 3. So we can put all of those in to the function notation of the derivative. Okay? And that will give us this. So if we go through and put them all in, what we're going to find is that we'll get something happening with a value. So if we do -3 to the power 4, -3 to the power 4 is going to be positive, isn't it? -3 to the power 4. So let's do 1 up here. -3. So we've got y dash. We're just going to check the first one. -3 to the power 4. -5. -3 again, because that's what we're checking. And I know it's a lot. It's a lot. Okay. These are even, so the positives are gone. So 3 3 threes are 9 threes are 27. 27 threes are 81. This is a positive, so it's going to remain a negative. 3 threes are 9, 45, plus 4, so 49. So our total is going to be 40. Now, what do we know about 40? 40, we can see on the first derivative, is greater than 0. It's positive. So the first derivative is a plus here. And we can go through and check them all. Now, at the value, that's going to be 0. And then what we're going to find is that it's changing. And because it's changing, and either side of this point here, we can say, well, that's a max. It's increasing, first derivative, then it's decreasing, first derivative. Okay, at this one here, x is minus 1, we're going to get a 0 again. And then what's happening here is increasing. Okay, so this is going to be a min. So now we're starting to identify what's going on. At 0, when we put 0 into the actual function value, we get a 4, and a 4 is a positive. So that's the same. There's no change there. When we put the half in, we get a positive. So it's plus, plus, plus. So there's no change. So that was an example of an exception of just checking one particular value not having any impact. So it just remained increasing, increasing, increasing. Okay, it's not until we get to x equals minus 1 or x equals 1 that we find, because that was a root, this is a max. Okay, that's a max. So we've gone plus, plus, plus up to a max. And guess what? When we check this, it's a minus. A minus, and then a 0. And in order for that to be a min, this one has to be a plus, which it is. It becomes a plus. So this becomes a min. So by doing this work, what we can say that in leading into minus 2, it's an increasing function. So it's got to be coming from below. Increasing. Up you go. Increasing. So actually I want to change that to black to match the exercise that we're doing. Analysing f dash of x. This is what this little table's doing. So we're seeing from the first derivative, it's increasing. Okay? Then after minus 2, it starts decreasing. What do you think is going to be happening? It's going to be going like this, isn't it? Then at minus 1, it's 0, and then it starts to increase again. Okay, it's increasing. Starts increasing, going up, 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 up. Okay, coincidentally, that's 1. I was a bit cheeky not telling you that, but that's going to be the y-intercept of this curve. And then as we approach 1, what's happening? Oh, we're plus, plus, plus. Increasing, increasing, increasing. Then we get to 0. And then we're decreasing, decreasing, decreasing. Oops. We'll have a change of concave down to 0, and then we start increasing again. So just by looking at the single derivative, the first derivative, we can establish the nature of the curve. So we've been able to do that, and your interval information is sound. All of your information is interval, and you can write all that down, of course. Okay? All right. So in a way, what that tells us is that we've determined their nature, okay, by looking at the intervals, and we've looked at why they're increasing and increasing because we've looked at f dash of x, first derivative. Now, the points of inflection. So the points of inflection are going to be the second derivative. So we set y equals 0. We set y double dash to 0. So y derivative, first of all, was, let's just get it back into the picture there, x4. So y double dash will be 4x3. 5 2s are 10. X and the 4 goes. So we've got 4x3 minus 10x. So we do set now. So we do solve. and we get 4x3 minus 10x is equal to 0. That's how we solve, isn't it? Now, when we solve these up here, it gave us where the m values were 0. When we're solving this one, it's going to tell us whether the values are concave up or concave down when we test all 4 values. So we'll have to test all those against this. So, and that will confirm what we thought from the first derivative. So just go ahead and do your undo, or before we do that, we'll take out what's common. I think a 2 is common. So that'll be 2x squared, 4x, that'll be a square, that'll make a 3, and 5. Okay, so when is this true? This is true when x is equal to 0. That's this one. When that's 0, the whole thing's 0, tick. Now, the other time is when 2x squared. So, 2x squared minus 5 is equal to 0. Undo. So a little bit of pre-work to do. It's not just going to jump out at us straight away. And so we've got to do a little bit of pre-work. Undo. So x squared is equal to plus or minus the square root of 5 on 2. Plus or minus the square root of 5 on 2. So they are our solutions. Root 5 on root 2. I can't simplify it, so I'll just leave it as root 5 on root 2. And minus root 5. Now, what is that telling us? What's happening at those x values? Okay, now if we put that back into the original y, I know, we will get the y version. So there's 3 x values, and remember we want to put them in to coordinate pairs. So x is going into the first slot, x, y. So these are our pairs going into the second slot, going into the third slot. What's the y value? Well, we've got to do this. We've got to go back to our original function, and we've got to put in 0, root 5 on 2. It's a lot, isn't it? And minus root 5 on 2. A lot of work. So put all the substitutions in, and by the time you get through all of those, we'll get the y coordinate. And the y coordinate for those is going to be approximately minus 0.7. So for 1, it's 1. For the positive root 5 on 2, it's minus, no, it's 2.7, approximately. And for the negative root 5 on 2, negative root 5 on 2, it's, so now we've got our pairs. So we've got 0, 1, da da da. So I'll let you finish those off. Okay? It's very straightforward. Alright, so if we go along and look at our pairs, our 0, that is a point of inflection. That's where it's changing from up to down. That's how that's looking. Okay? Looked, honestly. Okay, so 2.7, the next one. These root 5 on 2s are about 1.58. So 1.58. I'll do that. Okay, so the 1.58 is 2.7. So 1.58, it's 2.7. There it is. Ta-da! That is a point of inflection given by our coordinate system. So we've got lots of information. Now it's going swoop, swoop, change of concavity. Very good. The other one was minus 1.58, which is, look at this, 1.58, and it's near enough to minus 0.7. So it's just about here. So it's a bit of an exaggeration. It's a bit just about here, but this is a point of inflection. And so we get a and a dark one curving, concave down, concave up. Okay, so we're writing actually quite a lot of information in at this point, seeing if checking all of that. Okay, so we can do a table like this for f dash of x, double dash, or you can put that in if you want to. I'll leave that for you to do as an exercise, just to check all your values. So you put in your x and your f double dash at the x value you nominate, okay? And on an interval basis, you would be able to do a similar process, and essentially you'd be checking your intervals, and so you would build that up. So I'm going to, well, we've got 5. There's only 3 of them, isn't there? We've got 0, minus 5 on root 2, 0, 5 on root 2, minus 5 on root 2, minus 5. And so then you've got your interval. So we want the interval where it actually happens. Then we want the interval in between and where it actually happens, and the interval in between. So if we go and put all of those values in, what we'd expect is for these guys, there'd be a 0. So the derivative is 0, 0, 0. Okay, now below this, we'd expect the concavity to be negative in this interval. I'm going to let you put that interval in. You've got to get used to doing this. In this particular interval, concave is going up. You're testing a value in between 0 and negative 1.58. Okay, so you've got to check that. So check negative 1 plus positive 1.58. So you can check 1. You can check negative 2. Check 2. Okay, and as you do that, what you'll find is that you'll be getting information that's consistent with what we did over here. Okay, so all of that gives you your justifications for answering the questions above and below. Okay, so we've got negative is concave down, positive is a concave up, negative is a concave down, positive is a concave up. And all of those things are happening about there. Okay, so we can go in now and we can complete that sketch. All right. So let me just change a big bright colour, big limey green. And so what we do is we consolidate now. Consolidate that now. Okay. And so by using calculus, we've been able to draw a rather complicated function that we didn't know anything about, and beside that, we've been able to do that. So it's a lot of work, a lot of checking, and a lot of drudgery. It is possible for you to go and do A and B and then jump down to the second derivative. But where the questions ask you about increasing and decreasing, the answer is to be found in the first derivative. Okay, the concavity questions are to be found in the second derivative, and you'll get to recognise the intervals as you build those up. All right, lots of practice on Pearson will help you do that. All right, I'll come back and we'll start to finish this off. Thank you.